In this video, we focus on top-down miniaturization, carving smaller structures from bulk materials. In nanomedicine, we use two major approaches to create small structures. A top-down method, where we carve bulk material into micro or nanoscale structures, and a bottom-up method, where we build structures atom by atom, molecule by molecule. We can even combine both strategies into a hybrid process. In this video, we'll focus on understanding how top-down fabrication works. This module begins with the top-down approach. Here, we'll explore four top-down techniques: lithography, etching, milling, and ablation. Lithography uses light to pattern light-sensitive polymers called photoresist on surfaces like silicon or metals by changing the chemical integrity of the photoresist. Etching removes specific layers, either chemically or using plasma, to shape materials such as semiconductors or oxides. Milling physically cuts and sculpts metals, ceramics, or polymers into precise parts. Ablation, meanwhile, uses intense laser pulses to vaporize or carve away material, a physical change, and can be applied to both soft materials like polymers and hard materials like metals or ceramics. Lithography is a way to carve tiny patterns onto surfaces, like making microscopic circuits or medical devices. It's called a top-down approach because it starts with a bigger material and shapes it into fine details, usually using short wavelength light like UV or beams of electrons. Photolithography uses UV light around 365 nanometers through a mask to quickly copy patterns, but can only go down to about 200 nanometers. Deep UV lithography uses shorter UV light, about 193 to 248 nanometers, for smaller features around 20 nanometers, but costs more. Electron beam lithography skips the mask and draws directly with an electron beam, reaching features smaller than 10 nanometers. It's very precise but slow and expensive, so used mainly for research or custom nanomedicine designs. Laser direct writing also writes directly and is good for making custom biomedical chips. The resolution you can achieve in lithography depends not just on wavelength, but also on the quality of the system's parts and processes. For example, shorter wavelengths, mainly in the UV range or smaller, help make finer details because they can focus into tinier spots. Tiny features also need precise lenses or beams, special photoresists that hold sharp patterns and survive heat or chemicals, and stable equipment so vibrations don't blur the designs. It's quiz time! Stuck? No worries. Pause the video, check back on the previous slides, or feel free to Google it. Another top-down approach in microfabrication is etching. Etching removes material layers to create tiny patterns or structures. Unlike photolithography and its variations, like deep UV, electron beam, or direct light lithography, which use light to transfer patterns, etching relies on liquid chemicals, gases, plasma, or ions to shape materials. Etching comes in two types: wet etching and dry etching. Etching methods in microfabrication include wet etching and several types of dry etching. Wet etching uses liquid chemicals to dissolve materials. It's fast and low cost, but often isotropic, meaning it etches equally in all directions. This can cause undercutting, where material is removed sideways beneath the mask, leading to rounded features. However, in crystalline materials like silicon, wet etching can be anisotropic, etching faster along specific crystal planes and producing defined angles instead of smooth curves. For example, in silicon, the 100 planes etch faster than the 111 planes in potassium hydroxide, creating pyramid-shaped cavities with walls at about 54.7 degrees. Dry etching can be physical, chemical, or both. Physical sputtering, using ions like argon plus, physically knocks atoms off the surface. It's good for thinning or cleaning, but can introduce nanoroughness, typically around 1 to 20 nanometers RMS, which may be problematic in nanomedicine. Chemical dry etching uses reactive gases like sulfur hexafluoride or carbon tetrafluoride for silicon etching, or oxygen plasma and ozone for removing photoresist or cleaning. Combined physical and chemical dry etching, like reactive ion etching, ARIE, or deep reactive ion etching, DRIE, merges ion bombardment and chemical reactions, enabling directional, anisotropic etching with nearly 90-degree vertical walls. This is crucial for structures like microfluidic channels in nanomedicine devices. Although more complex and costly, dry etching provides the precision needed for advanced nanomedicine applications. Accurate etching data is crucial in microfabrication. For details on wet and dry etch rates, crystal effects, and other parameters, I recommend these references listed here on the slide. You can click the links provided to access these valuable benchmarks for fabrication planning. It's quiz time. Milling is another top-down microfabrication method used to shape materials into precise structures. Unlike lithography or etching, milling removes material by directly machining the surface. This can involve physical tools like microdrills and blades, or energy-driven methods like focused ion beams or scanning probe tips, which remove material through physical bombardment or localized force. Milling is especially useful for creating fine details in metals, ceramics, or polymers, and is chosen when mechanical precision and surface quality are critical. Let's compare focused ion beam, or FIB, and AFM-based nanomachining, two advanced nanofabrication methods often grouped under milling because they physically remove material to shape patterns. FIB uses a beam of ions to sputter material or directly write features as small as 10 to 50 nanometers, working on metals, semiconductors, polymers, and ceramics. It's precise but slow over large areas and can implant ions into the surface, which might change material properties. AFM-based nanomachining uses the tip of an atomic force microscope to physically scratch or sculpt surfaces with nanoscale precision, typically between 10 and 100 nanometers. It's ideal for soft polymers, thin metal films, or biological samples, but extremely slow because it works point by point. In nanomedicine, FIB and AFM nanomachining help create features like nanopores, nanochannels, and grooves to guide cell behavior. It's quiz time. Finally, ablation is another top-down microfabrication technique we will discuss in this submodule. Unlike lithography, which uses light to pattern surfaces, or etching, which removes layers with chemicals or plasma, ablation uses intense energy beams, either light energy, photons, or kinetic energy, to directly remove material. And while some milling techniques also use energy beams, ablation typically removes material by rapid vaporization rather than cutting or sputtering, making it ideal for precise, contact-free shaping of metals, ceramics, or polymers. Laser ablation uses pulsed light energy to precisely vaporize materials like polymers, ceramics, metals, and glass. It achieves resolutions from around 100 nanometers to a few micrometers and is maskless, with minimal heat when using ultrafast lasers. In ultrafast laser ablation, ultrafast refers to extremely short laser pulses, often in the femtosecond range. These pulses deliver high energy in brief bursts, vaporizing material precisely while minimizing heat damage. Although scanning speed affects how fast surfaces are processed, ultrafast here mainly describes the pulse duration, not the scanning speed. Laser ablation's depth is limited, and it's slower on metals. In nanomedicine, it's used for surface patterning, microfluidics, and modifying biomaterial surfaces, valued for creating precise cuts and textures. It's quiz time. In this module, we've discovered how top-down miniaturization transforms solid materials into tiny micro and nanoscale designs. With tools like lithography, etching, milling, and laser ablation, we can craft intricate structures that power sensors, medical implants, drug delivery systems, and cutting-edge cellular studies in nanomedicine.